Okay, any questions? Any questions about anything? Questions? Okay. So today what I want to do is wrap up the discussion of the DTFT, and that's chapter 7 in the book, and then move on to chapter 8, which is the DFT. Not to be confused with the DTFT, and I'll try to emphasize that as we go along. But anyway, what did we do last time? We talked more about the DTFT, and when you've got this kind of a situation going on, where you have a signal x of n and a DTFT x hat of omega hat, I tried to sell you on the idea that x hat of omega hat reflects the frequency content of x of n, whatever that means when x of n is not a sum of sinusoids. And so we got sold on the idea that x, I hope you got sold on the idea, I was trying to sell you the idea, but anyway, x hat of omega hat represents the sort of the quote-unquote frequency content of x of n, and so people call it the spectrum of x of n, and they also call it the frequency domain description of x of n. They also call it the spectral representation of x of n. All those things mean the same thing. And we sold you, or I tried to sell you again, on the idea of an LTI system, at least one with a frequency response, say h hat of omega hat, acts like what I called a frequency selected filter. And there were two ways of looking at that are related, but I don't want you to conflate them. One, it was a picture. In one case, we had a pure sinusoid goes in, then h hat at that frequency at times a pure sinusoid comes out. That's one picture. Another picture, let me just draw them just one more time. Don't conflate these two pictures, that if I take e to the jn omega 0 hat and put it through the system, what comes out is this. And if I put x of n into the system, then what comes out is equal to y of n, and x of n has DTFT x hat of omega hat. Y of n has DTFT, which is the product of the frequency response of the system with the DTFT of x. And the reason those two pictures aren't the same at all is this signal here doesn't even have a DTFT, at least in this class. In some classes you'll have delta functions, Dirac delta functions. We had a little Dirac conversation last time. But in this class it doesn't. So anyway, all right, so now I want to move on, and I want to talk about the most awesome radical filters of all, the ideal filters. And it turns out these are things you can't build for reasons we shall see. Okay, so what about ideal filters? First, I'll talk about the ideal low-pass filter. And you can construct an ideal high-pass and ideal bandpass in the same kind of way. So we're going to focus on the low pass for now. So what is an ideal low pass filter? It's a filter. And by the way, you know, depending on where you read, low pass can be two words without a hyphen, or it can be a hyphenated two-word thing, or it can be one word, low pass. I like to write it this way. Ideal low pass filter has frequency response that looks like this. And what I'm going to do, I'm going to graph it over a certain range of omega values that's bigger than the usual minus pi to pi, just so you see the periodicity. So here's 3 pi, and then here's minus pi, minus 2 pi. Like so, it's going to have h hat of omega hat is going to look like this. It's going to have height 1 over the range, and whatever you want to call these frequencies, I'm going to call this omega hat sub b, and minus omega hat sub b. The book calls them omega hat sub CO, meaning cut off, but that just gets really messy after a while. Okay, and it's going to repeat, remember, because frequency responses are DTFTs, and they are therefore periodic in omega hat. So it's going to look like this. And what is this frequency? This is minus 2 pi plus omega hat sub b. This frequency here is 2 pi minus omega hat b, 2 pi plus omega hat b. There you go. That's the ideal low-pass filter. And this is 2 pi periodic. This h hat of omega hat is, as are all DTFTs, 2 pi periodic in omega hat. Okay. Now notice, it's unlike most DTFTs, this h hat of omega hat is actually real value. It doesn't have any complexness to it. It doesn't have any phase, anything like that. That turns out to be, in a sense, what makes it impossible to build. So why can't we build a system, a causal LTI system, that has that as its frequency response? Well, we've seen before that the h of n that goes with this h hat of omega, so the signal h of n, whose DTFT is this h hat of omega, at is this h of n equals sine of n omega hat b divided by pi n. And this is for all n. That was one of our examples we did. We found this using the so-called synthesis equation for the DTFT. This h of n, so since h of n is not 0 for all n less than 0, comma, it is not the impulse response for a causal system. Another way of saying that is the following. The system whose impulse response is h of n and this is the same system whose frequency response is h hat of omega hat above. So whose frequency response is this h hat of omega hat above, is not causal. Why is it not causal? We discovered earlier on when we talked about causality of LTI systems, FIR systems or general LTI systems. Causality of a system is the same as saying that its impulse response is 0 for times less than 0. Why is that the case? Well, think about the experiment. You walk into the room and you kick it at time 0. It couldn't have been doing anything before that if nothing was going into it, and the system was causal. So anyway, it's not a causal system. Thus, we can't build an actual system that has that ideal low-pass frequency response. So thus, we can't build this system. And let me just say that the same is going to be true for, you can probably guess what an ideal high-pass filter frequency response looks like, ideal bandpass filter frequency response looks like. Let me just draw the pictures. So the same is true for ideal high-pass. And here's the frequency response of an ideal high-pass filter. So this is pi, this is 2 pi, this is 3 pi, minus pi, minus 2 pi, so on. Ideal high pass is going to have a frequency response that looks like this. See the difference there? On the interval minus pi to pi, it, quote unquote, we'll get to this in a minute, passes the higher frequencies and kills the lower frequencies. And an ideal bandpass is going to look like this. So, or ideal bandpass. So ideal bandpass, pi, 2 pi, 3 pi, you're going to have this kind of thing going on. Okay, and I'll refer back to these pictures in a moment. And just for definiteness, let's put a 1 here, just so you know that's going to be true. All right. Now, as usual, what we're going to do is focus on the interval minus pi to pi. Okay, so focus on these frequency responses on the interval minus pi less than or equal omega hat less than or equal to pi. So the ideal low pass is going to look like this. It's going to go out to plus and minus omega hat b, and then out here pi minus pi. It's going to be 0 there and 1 here. The ideal high pass is going to look like this. Here's pi, it's going to be like so, minus pi, it's going to be like so. Okay, and the ideal bandpass, I'll just leave that on the side for now. All right, so why do we call this a low pass and this a high pass? Remember the rationale for frequencies near 0, closer to 0, in the interval minus pi to pi, we think of those as low frequencies. Frequencies out near plus and minus, or out near pi, we think of as high frequencies. Why? Because of this background picture that you sampled, signal, band-limited continuous time signal faster than Nyquist rate, and I drew pictures of that, I think, 2 lectures ago. So this guy has a frequency response that's 1 over the low frequency range and 0 over the high frequency range, whereas this guy is just the opposite. Has a frequency response that's 0 over the low frequency range and 1 over the high frequency range. What do these systems do to input signals? Let's look at these 2 pictures and answer that question. So, what happens when I put a pure sinusoid of frequency omega hat, so e to the j n omega 0 hat, into one of these systems, what's going to come out? Anybody care to hazard a guess? Let's be definite. This is the low pass. Let's put the low pass system. So we're talking about that graph up there. What comes out when I put a pure sinusoid of frequency omega 0 hat into this system? Okay, you're right. It does depend on omega 0 hat. How so? Ian? Yeah, exactly. If omega 0 hat is between omega hat b and minus, or if omega 0 hat is less than omega hat b, then this thing goes right through. So what comes out of here is either going to be the signal itself when omega 0 hat is less than or equal to omega hat b, and 0 otherwise. And here I'm assuming that omega 0 hat is in the interval minus pi to pi. In other words, the low-pass filter passes unadulterated all pure sinusoids whose frequencies lie in the interval minus omega hat b less than or equal to omega hat less than or equal to omega hat b. And it kills, annihilates, all the pure sinusoids whose frequencies lie in omega hat b less than or equal to absolute value of omega hat less than pi. Remember, I'm assuming omega 0 is in the interval minus pi to pi. Okay? It passes all the low frequency sinusoids and annihilates all the high frequency sinusoids. And this is why people call, this is really imaginative terminology here, this is why people call, so terminology, we call the interval minus omega hat b up to omega hat b the pass band. And again, this is a word that some people write as one word without a hyphen, or two words, or a hyphenated pair of words, as I do here. And the interval omega hat b, intervals actually, it's a union of intervals, omega hat less than pi, the stop band of the filter. So the filter passes sinusoids whose frequencies are in the pass band. It kills sinusoids whose frequency is in the stop band. And you could go to the high pass and the band pass and define pass band and stop band similarly and see what they do to sinusoids. They pass them if the frequency is in the pass band. They stop them if the frequency is in the stop band. What if I apply another kind of input to this system, not just a pure sinusoid, but some x of n that has a dtft x hat of omega? So if you drive the ideal low pass with a signal x of n that has a dtft, so this is using the other half of the don't conflate thing that was on this board before I erased it, x hat of omega hat, comma. Then you get an output signal. So then the output, y of n, has dtft, y hat of omega hat equals h hat of omega hat times x hat of omega hat. And if you look and see what h hat of omega hat is, it's 1 between plus and minus omega hat b. There's a missing label on that. Let me just draw it in. It's minus omega hat b. It's been bugging me for the last couple minutes. Yeah, I know. I'm a little bit OCD about the boards. I saw a good T-shirt along those lines. It says, "Does anal retentive have a hyphen?" Question mark. So that's a good T-shirt. Anyway, thus, y hat of omega hat equals x hat of omega hat when omega hat is in the pass band. So omega hat is in the interval minus omega hat b up to omega hat b. And it equals 0 when omega hat b is less than or equal to absolute value of omega hat less than or equal to pi. What does this say to you? This says to me that the ideal low-pass filter passes unadulterated the part of the frequency content of the input signal x as embodied in its dtft that lies in the pass band, and it kills the part of the frequency content in x that lies in the stop band. so I'll put that in quotes. The filter passes unadulterated all the frequency content in the input signal that lies in the passband, and it annihilates the rest. All right. And you can go through the same kind of thing for the high pass and the band pass. And all the changes is the meaning of pass band and stop band in each case. Okay? Good. So now we know how these filters operate on signals. And we know that we can't build them because they have non-causal impulse responses. So how do you build good low-pass filters that are real-life things that you can actually, put on a chip or code into a computer or something like that? And the book has a nice little section or two on that, and I want to talk about that now. And I'm going to speak here in rather general terms. I'm not going to be real well, actually I'm going to be a little more mathematical than the book is, but not as mathematical as usual about these. Okay, so how do you, let's focus on the low pass. Since the ideal low pass isn't a causal system, what we want to do in practice can only approximate it with actual causal systems. And there's lots of ways of doing that. And you could say, without being too inaccurate, that the major focus of classical DSP is building good low-pass filters. Okay, so a major focus of quote-unquote classical DSP, DSP meaning digital signal processing, is coming up with decent approximations to an ideal low-pass filter. So major focus of this is on designing filters with frequency response, say h hat omega hat, that are close to that ideal low-pass characteristic, such that, first off, the magnitude of h hat of omega hat is roughly equal to the magnitude of what I'll call the desired frequency response. Desired meaning this is the ideal low pass. So we want ones whose magnitude is pretty close to this and whose phase is not too bad, whatever that means. Not too damaging. So phase of h hat of omega hat is quote unquote not too damaging. So that's a really precise mathematical expression, right? Phase is not too damaging. What does that mean? You can, I could go on and on about this, but one could argue that what makes these things physically unbuildable, what makes them non-causal systems, is that their frequency responses don't have any phase. That any frequency response you can actually build is going to have phase, right? And so you're building a system that has phase, and we want the phase not to be too damaging. And it turns out that not too damaging can mean a number of things, but often means what? It means that the system is actually what we call a generalized linear phase system. We've seen this already. Okay, so now I want to look at, think about this low-pass filter. So let's graph h desired hat of omega. Let's do it big. So here you're going to have pi, here you're going to have minus pi, and here you're going to have minus omega hat b, and plus omega hat b. And the ideal filter has frequency response this. So this is h desired hat. And what is the h hat of omega magnitude going to look like? So here I'll do the little schematic up here. This is h desired hat of omega hat. And what I'm going to draw that has ripples in it is h hat of omega hat. What is it going to look like? It's going to look something like this. It's going to have ripply stuff going on, and then it's going to go up and over, and then there's going to be ripply stuff in here. It's all going to be very symmetric. It's going to go down, and then there's ripply stuff out here. All right. Oh, and actually, this is magnitude. It's going to look like that. All right. Now, the various imperfections here in this picture, obviously, in the approximation with the magnitude to the ideal magnitude, the desired magnitude. And people give names to these things. Okay, so they call this guy, this ripply behavior in here, they call it passband ripple. Big, creative naming of thing, okay? And they call these guys here, guess what? Anybody want to hazard a guess what they call those ripples? Come on, somebody. Okay, back row Sam. Yes, that's right, stop band ripples. So stop band ripple, actually. And they call this slantiness here, the fact that it doesn't go straight down to zero, they call that roll off. And I usually write that as one word without a hyphen for whatever reason. Not to be confused with rule off, place in College Town. And they call the place where the roll off is happening the transition region. Okay, so basically designing a good, buildable approximation to an ideal low-pass filter, what you do is you look at all these imperfections. You look at the passband ripple, the stop band ripple, the roll-off, the width of the transition region, and those things, it turns out, all trade off against each other. Okay, I want to emphasize that. They trade off against each other. Like if you design a filter that has a really good, really narrow transition zone, then it turns out that the Gibbs phenomenon is going to cause like a huge ripple right at the edge, something like that. So it turns out all these imperfections trade off against each other. So you make one better, you make another worse. Whack-a-mole filter design. And the history of DSP is littered, I shouldn't say littered, that sounds really negative. It's full of great ideas for how to trade these things off in a way that's not too bad. Like you get an equi-ripple filter, that's a good thing. It doesn't have a big ripple at the edge and little ripples in the middle. It has about equal. Those are kind of desiderata that people look at. And one of our former faculty members, Tom Harks, who's now retired, came up with a famous algorithm. Okay, so many algorithms for coming up with filter coefficients where these trade-offs help. So filter design algorithms. And one famous algorithm is so-called the Harks Mcclellan algorithm. And I think I might have even mentioned this the first day of school when I was telling you about the book we're using. We're using a book whose lead author is Jim Mcclellan, Georgia Tech professor, who, along with Tom Harks, Cornell professor, but he was actually at Rice at the time, came up with this Harks-Mcclellan algorithm. So Mcclellan is the author of your book. Okay, so that's the general comment. Now I want to talk about a specific way of designing filters, designing a low-pass filter. And that's called windowing. So, and this is the one that the book goes into in a little bit of depth. And when we talk about spectrograms later on, we're going to be touching back on it. So one approach that's easy to understand is called windowing. Okay, so what is windowing? What is the goal of windowing? The goal of windowing is to design a causal FIR filter whose frequency response is of this kind that I mentioned over there, whose frequency response approximates h hat desired of omega hat in magnitude, and whose phase is not too damaging. So it designed a causal FIR filter that works in the sense of, and let me just go over and mark this pair of things star, okay? In the sense of those two criteria, star. But magnitude is a good approximation of h hat desired of omega hat, and the phase is not too bad. And as it happens, what we're going to come up with here is actually a generalized linear phase causal FIR filter that does it. All right. So how do you do windowing? How do you do windowing? Well, first thing you do is you pick a window length. Okay? And that's going to be some positive integer L. So what do? You pick, or actually L's not going to be the window length. So first step is you pick L bigger than 0, so that if you shift the desired impulse response to the right by L, then most of the action in the impulse response takes place in the interval 0 through L, not including L. So that the following is true. If you shift h desired of n, and remember what h desired of n here is? It's sine of n omega hat b over pi n to the right by L. Wait, I don't want to do this wrong. I want to do this right. So what happens here when I do this discussion is I swap the roles of L and N sometimes. So I want to make sure I don't do that here. So you'll pardon me if I have a look at my laptop. Oh, that's not good. We're going to pick the L is going to be the window length. So let's just erase this part. Okay. First pick L bigger than 0 so that most of the action I feel like I have to do this from scratch every time. It's so frustrating. Okay, let's do it this way. Okay, I'm gonna pause for a second here. Collect my thoughts. When did this lecture start? Was it 35 minutes ago? Was it 30 minutes ago? I think it was 35 minutes ago. So this is like the 3-minute break. All right. So pick an odd integer L. Positive integer L, so that most of the action in h desired of n and this is a qualitative thing. What most means depends on how precise you want to be, whatever. We'll see what happens when we raise L, etc. In h desired of n, which remember was sine of n omega hat b divided by pi n. Most of the action in this takes place in the interval, the time interval of length L centered on time 0. So here you've got this sinc function, right? If you did a stem plot, it would look like this, going out like all the different values of n. So you pick your L so that this interval of length L is going to be your thing. Okay? So this is going to be of time L minus 1. This is going to be time minus L minus 1 over 2. If you shift h desired of n to the right by L minus 1 over 2, so next, what you do is shift h desired of n to the right by L minus 1 over 2. Okay. What does that do? That slides that high activity interval so that it starts at time 0. And then you window it. You window it. On the interval of length L starting at 0. So i.e., what you do is you chop all of it away except the part between, how about this, the part where 0 is less than or equal to n is less than L. And you keep the rest. And the way I'm windowing here, i.e. we set h of n, this is going to be the impulse response of our system that has frequency response h hat of omega hat that's good in terms of the star criteria. We set h of n equal to this. H desired of n minus L minus 1 over 2 when 0 is less than or equal to n less than L and 0 otherwise. Okay? That was a little tortuous, but that's the correct formula. So essentially what we've got here is we've got an impulse response that has finite duration, duration's length L, that has all the high activity part of the desired impulse response, but shifted to the right by L minus 1 over 2, where L is a user choice. Okay? Now, let me just comment here that the way I've defined this h of n, the windowing that we've done here is what's called rectangular windowing. Why? So here's a comment. Note that you can write h desired of n h of n as h desired of n times a windowing function. W of n, where W of n is the windowing function, the rectangular windowing function given by the following formula. W of n is equal to 1 when 0 is less than or equal to n less than L, and 0 otherwise. So it's called a rectangular window for obvious reasons. It's 0 for time less than 0, then it goes up to 1 for L time steps, and then it's 0 after that. It turns out that in applications, people use other windowing functions instead of the rectangular one, but they all share some traits. And I'm just going to tell you the names of a couple of the others. The book only goes over one of them, but if you look at any DSP book like Oppenheim and Schaefer, you see all these different windowing functions. So in practice, there are reasons associated with the trade-offs between the ripples and the transition width and all that stuff for using other windowing functions. So in applications, people are always coming up with new windowing functions. So people use other windowing functions. And in some sense, these windowing functions are, you might call them kinder, gentler windowing functions than the rectangular. They don't just chop. They chop sort of gently toward the edges. Like in the middle, they pass through, and then they just chop sort of in a slopey kind of way. So these are sort of kinder and gentler than the rectangular, which just chops. And two examples are the so-called Hamming window. That's the one the book talks about. And the Hamming window is named after Richard Hamming, who was a famous coding theory guy who spent most of his career at the Naval Postgraduate School in Monterey, California. Okay? And one of the big awards in the IEEE Information Theory Society is called the Hamming Medal, the Richard Hamming Medal. And you might have heard of Hamming distance. How many people have heard of Hamming distance? Okay, are you all CS majors? No. Okay, so even ECs have heard of Hamming distance. Hamming distance between two bit strings is the number of positions in which they differ. And it's a good way of measuring how different two bit strings are. So Hamming window, and there's another one named after a German guy named Hahn, H-A-N-N. And because Hahn looks like the beginning of Hamming, some people call this the Hanning window, H-A-N-N-I-N-G. I think that's kind of funny. Window. And those are two examples of windowing functions, W of n, that people use for this windowing operation. So what happens when you do this? What are the user choices here? Well, there's only one really. Okay. Say we do rectangular windowing. So say we're doing back to the rectangular window. So back to the rectangular window. The one user choice that you've made so far is L. And that's the window length. That's how much of the desired system's impulse response you decide to keep and incorporate into your design system. So larger L means that you, quote unquote, keep more of h desired of n when you in h of n. You keep a longer segment of the desired impulse response in h of n. What you discover is the following. It turns out that the system you get, the h of n you get by doing this process on the ideal low-pass filter, rectangular windowing with a window of length L, shifting the stuff to the right by L minus 1 over 2. It turns out that that system is a causal FIR system. So clearly, the system you get, the system with impulse response, h of n above, is causal. And that's because h of n equals 0 when n is less than 0. FIR, and that's because h of n is equal to 0 when n is bigger than or equal to L. And bonus has generalized linear phase. So it's GLP. What you find is that h hat of omega hat is roughly equal to h hat desired of omega hat. That's the frequency response of the ideal low-pass filter. That's just a 1 in between, plus or minus omega hat b, times e to the minus j L minus 1 over 2 omega hat. And the approximation here is better the larger L is. Okay. So that's one approach to building a decent low-pass filter. Now, if you think about it, what's going on here? When you put a sinusoid through this system, what happens to it? By virtue of this approximate equality here, it passes through almost unadulterated, except for a delay. Why the delay? Because of that e to the minus j L minus 1 over 2. So let's, omega hat, so let's see what's going on here with that. Essentially what we've got here, our design system approximates this cascade. Ideal low pass, followed by a time delay of L minus 1 over 2. Okay? The bigger L is, the better the approximation of the magnitude is to that of an ideal low pass, but the longer the delay is. Okay? So thus, bigger L means better approximation above, but at the cost of longer delay. So if you want a system that sharply kills, say, every cosine, say, with frequency bigger than 60, no, it has to be between minus pi and pi, whatever. Sharply kills every cosine outside of this range and passes unadulterated all at once within this range, but you don't care about the delay. Then you make L really big, right? But if you need something speedy to happen, then there's a trade-off there. Okay, so that's just some general comments about practical building actual low-pass filters in real life and building them so that they are FIR, causal obviously, they have to be causal. FIR is good. And generalized linear phase is like the icing on the cake. Okay. So that's just some general comments. You can look at the book for more. detail, examples, etc., including they point you to some MATLAB filter design stuff that's in the DSP toolbox, whatever. All right, so that pretty much ends the material in Chapter 7. Any questions about this stuff before we move on? Questions? Okay, so now is the time. Oh, sorry, Bryce. Actually, I don't know the answer to that question. Don't know the answer to that question. Any others? Okay, so let's move on. That's the end of the material in Chapter 7 that we're going to cover in lecture. And now let's move on to Chapter 8, which is the DFT, discrete Fourier transform. And here I want to warn you guys, this is very important. I do this much differently from how the book does it. Okay? And I think my way is a lot better, of course, but you know, I want you to be careful. Be careful. This is more than just the h of e to the j omega versus h hat of omega hat thing. You know, this is worse. This is more of a teacher departure from book problem than we've encountered so far. So I will warn you in all caps here. So on now to the DFT, Chapter 8, and caution, all caps, that my way is much different from books way. My way. Oh, actually, I was last night. My sister and one of my sisters and her husband and her family and my brother and I were playing an online game together. Like, anyway, just to, you know, be family, to spend some family time when we can't visit, and it turns out that in the Philippines, I don't know how many of you know this, but apparently there's this string of murders that occur at concerts or weddings called the My Way murders, where it's because when the song "I Did It My Way" by Frank Sinatra is sung, then someone gets killed. Something along those lines. It's really bizarre. But anyway, when I wrote up My Way, I thought of that thing. Anyway, all right. So My Way is much different from the books. All right. So My Way is based on the concept of what I call, and what most people call, an endpoint signal. Okay, so we start. This is our starting point. Starting point is the notion of an endpoint signal. Okay, what is an endpoint signal? It's a whole signal. A whole discrete time signal. So we say that x of n is an endpoint signal when what? X of n equals 0 when n is less than 0, and x of n is equal to 0 when n is bigger than or equal to n. Now, I want to emphasize, it's my way of doing this. An endpoint signal is a whole signal. It's not just a piece of a signal. Okay. So, note, an n-point signal is a whole signal. Okay? Not just a piece of a whole signal. Now observe that if cap m is another integer that's bigger than n, and x is an n-point signal, so x of n is an n-point signal, then x of n is also an m-point signal. It's an m-point signal that just happens to be 0 between times n and m. So it's one that just happens to be 0. I'll do some examples in a second. It happens to be 0 4 times little n bigger than or equal to cap n less than cap n. All right, so let's do some examples. So e.g. How about x of n is given as follows. X of n is 0 when n is less than 0. X of 0 is 3. X of n is equal to 0 when 1 is less than or equal to n less than, say, 7. And x of n, x of 7 is equal to 19, and x of n is equal to 0 when n is bigger than 7. How about that? Okay, so let me ask you guys. Is x of n a 2-point signal? How many people think yes, x of n is a 2-point signal? How many people think no? Okay. As always, abstentions win. Okay. What is an n-point signal? It's a signal that's 0 for negative times, and certainly this x satisfies that. And it's also 0 for time bigger than n. Now, clearly when n equals 2, you still have stuff happening in x. You have stuff happening out at 7. So x of n is not a 2-point signal, even though it's only 2 non-zero values. Only 2 non-zero values are 2 times, 0 and 7. So here's some things to note. Let's sing some truths. Truths. Okay? X of n is a 7-point signal. Right? Because it's 0 for time less than 0, and 0 for time, or an 8-point signal, actually. And an 8-point signal because, this is because x of n equals 0 when n is less than 0, and x of n equals 0 when n is bigger than or equal to 8. Okay, so x of n is an 8-point signal. X of n is not a 2-point signal. So it's not a 2-point signal, even though it has only 2 non-zero values. Okay? And is x of n a 13-point signal? Yes. Yes. X of n is a 13-point signal because it's 0 for times less than 0 and for times bigger than or equal to 13. So truth number 3. x of n is a 13-point signal. That just happens to be 0 for 8 less than or equal to n less than 13. Okay, so those are some truths about x of n, when x of n is defined that way. Now, for me, regarding an n-point signal as an m-point signal for every m bigger than n, that is just a different way of viewing the whole signal x of n. Okay, so note that if you have an n-point signal, viewing an n-point signal as x of n, let's call it x of n, as an m-point signal for some cap m bigger than n, for us is just quote unquote like looking at the same whole signal x of n in two different ways. In one case, you think of it as an n-point signal. In the other case, you think of it as an m-point signal. But in signal processing and data science and machine learning and all those places where all these things come up, regarding an n-point signal as an m-point signal for m bigger than n, people call that process zero padding. Okay? So in practice, all right, in practice, people call this, quote unquote, view n-point as an m-point for some m bigger than n. They call it zero padding because what they've got these n numbers that correspond to the n possible non-zero values in an n-point signal, and what they do is they extend it to a string of numbers of length cap m by just tacking on a bunch of zeros. So here's the idea. The pertinent values, pertinent, that's not a good word here. How about the only important values? Of the endpoint signal x of n are the values x of n for 0 less than or equal to n less than cap n, and you take the string of values. So you tack on m minus n zeros. We use the Greek surname spelling of zeros to get the only important values of x of n viewed as an m-point signal. Okay, so maybe I'm beating a dead horse here. The thing is, the book does this so differently. I really like to think of endpoint signals as whole signals. They are discrete time signals that just happen to be 0 outside of the interval 0 to n minus 1 inclusive. And notice that the interval here that we use, 0 less than or equal to n less than n, it's a very Pythonic kind of way of writing the interval. And if you want to think MATLAB, you have to think 1 through n. But this is the customary way to do it. Certainly the way I like to do it. Okay, so a couple comments about endpoint signals. if you take two endpoint signals and take a linear combo, do you get another endpoint signal? Yes, no, maybe? Yes. So note linear combos of endpoint signals are also endpoint signals. So in the vector space of all discrete time signals, the set of all endpoint signals, cap endpoint signals, is a subspace. It's closed under taking linear combos. Okay? Right? All right. So that's one global thing. All right. But notice that time shifts of endpoint signals are not endpoint signals necessarily, because if you shift an endpoint signal to the right by some amount, then you're going to usually cause values, non-zero values of the signal to penetrate times bigger than cap n. So it's not a closed under shifting set of discrete time signals. However, if we do a different kind of shifting, we get an operation on endpoint signals that's shift-alike. And that's called cyclic shifting. Okay, so now I want to talk about some things you can do. So to understand some other operations you can perform, other ops on endpoint signals, what we need to do is I want to introduce you to some notation that you've probably seen before. We need to view a bit of modular arithmetic, just a teeny bit. Modular arithmetic, and this is something that, how many people have seen modular arithmetic before in some class? Yeah, like 3 mod. Okay, let's just dive right in. If I write this, so given an integer cap n, say bigger than 1, if I write k mod n, like so, I'm going to read this, quote, k mod n, where k here is another integer, positive or negative. What does that mean? Does everyone know what that means? If someone came up to you in Whole Plaza and said, I want to take, well, you know, no, I can't think of a good Whole Plaza question for modular arithmetic. Let me just write up a couple and see if you know. So what is, for example, what is 3 mod 7? What's that? Quick. 3, yes. What is 7 mod 3? Taking a look. 1. Very good. Okay. What is minus 3 mod 7? That's a little hard. Hannah. 4, yes. How did you know? Okay, that's as good a reason as any. Okay. How about what is, I think that's enough. I think you guys know what it is, right? Basically, to get k mod n, you shift k in whatever direction you have to shift it by multiples of cap n until you get in the interval 0 through n minus 1, and where you land is k mod n. So let me just write that down. We've done a lot of shifting and landing this semester, haven't we? No, we did with F's, we did with omega hats, now we're doing it with K's. Shifting and landing. So to get k mod n, you shift k up or down by n repeatedly until you land in the magic interval 0 less than or equal to n less than n, and where you land is k mod n. So when Hannah said that minus 3 mod 7 is 4, what she did was she took minus 3 and she added 7 to it and got 4. You add 7 to minus 3, you land in the interval. And if the number inside, if k is bigger than n, you can also think of that k mod n is the remainder when you divide k by n. But that doesn't work quite when k is minus 3. All right, so that's k mod n. So what does modular arithmetic help us with here? So given an endpoint signal x of n, so an endpoint signal x of n, and some n0, where 0 is less than or equal to n0 less than cap n, the cyclic shift of x of n by n0 is the signal y of n given by the following formula. Y of n equals x. It's equal to 0 when n is less than 0, and when n is bigger than or equal to cap n, and it's equal to x of what? N minus n0 mod cap n, when n is in the magic interval 0 to n minus 1. Okay. So that's the cyclic shift. Now let me just, I think I'm running out of time here, but I'm not 100% sure. Really need to write down when I start, okay? Come on. It's supposed to come up when I do that. There's something else. Okay, we're going to quit for today, and I'll pick it up next time. I'm going to figure out how to stop this recording here. I don't know what's going on.